All right, it's 10:31, and students, we've got a ton of stuff to do. We're gonna we're gonna be working like maniacs today. So just batten down the hatches, get your clicker out, get your calculator out, get your notes ready, and we're gonna do some deluxe thinking and some deluxe problem solving with calculations. And even if danger is your middle name, then you should be set. Otherwise, just get ready to roll. Now, first things first. Derry had customers yesterday at her office hours, and those are from 1 p.m. to 2 p.m. on Mondays. And as I always say, if you can study with another human being every week, even for half an hour, it will definitely help you because on my exams, as you now know, they are not cinchy. You've got to think. I mean, if you want to get an A, if you want to ace it, you've got to be on the top of your game. And the top of this game is being able to think your way through and having a study partner, whether it's Derry, whether it's me, whether it's your roommate, someone in the class, someone in the afternoon class, or SI, someone you meet over in SI, that is always going to help you. All right, last time we were talking about momentum and impulse. Here's the impulse equation. Go ahead and write that down at the top of your notes for today. We're going to be using that. And we're going to be doing some calculations with that. That's our target calculation, just to reinforce that. And just let me repeat what I've already said. This is another version of Newton's second law. It's not like, oh, this is, some alternate view of reality. It's not. It's Newton's second law kind of recast in the language of momentum, which he definitely was familiar with. So get your clicker out. Let's reinforce with an example. And we'll just go step by step. And we'll fill in some of the specs, and then we'll hit the impulse question. And take good notes. What we're going to do is compute the impulse on a basketball in free fall. So go ahead and sketch a vertical axis, a y-axis, if you will. And we're going to do a time increment, delta t, of a quarter second, 0.25 seconds. Just for a round number. There's nothing magical about it. I just thought, well, we'll do something here that's not too bodacious, and 1 second's a little bit more than I wanted, so 0.25 ends up being pretty good. But before we do that, I want to, Sir Isaac Newton and I both want to trot you through a few of the specs for this problem, some of the basics. Now, it wasn't basic for exam 1, but it's going to be basic on exam 2 and following. First of all, what's the weight force of a NBA basketball? Its mass is 0.62 kilograms. And let me start the question. This is multiple choice. Okay, you should be able to answer it now. And you're going to need your calculator. If you don't have a calculator, use your cell phone. You can't on a test, but in lecture, of course, you may do it. Consult with your neighbors. This is a basic calculation. By the end of the semester, you're going to be able to do this one in your sleep. Maybe even your roommates that don't take this class will be able to do it in their sleep. 30 seconds. Hurry up, you guys. We're clicking. Move it. Would you guys like to dismiss early today if we can? A few minutes? Yeah, okay. I think we might. I'm not sure, but I think we might. But we got to get these specs done. 10 seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. All right, let me zip this up. Yeah. Uh-oh. What? What is... You know, here's the answer distribution. The correct answer is C, 6.076. I can't remember why I put down 0.155 newtons. Usually I try to tempt you, but this one was obviously, A was obviously tempting for a bunch of you. I cannot remember why I put that particular number down. But what, okay, the time. Now what I want you to do is jot down those answers carefully, because I'm going to give you a little test-taking IQ test question here in just a second. So jot down A, B, C, and D, and make sure to circle the correct answer, C, because my question for you is, why or how can you eliminate the other three options? In other words, option C is the correct one. Okay. And you know, on my exams, a lot of the time, if I give you a multiple choice question with numeric values for the answers like this, they're all a number of newtons. Usually I set them up so that even if you don't have a calculator, but you have a brain operating, you can kind of figure out why they, you know, at least one or two of them can be eliminated. And that's always a good strategy. So talk it over with your neighbors, because I'm going to ask you a question about it in just a second. All right? Why do you think that? Because on an exam, you want to be able to say, all right, I can eliminate B or I can eliminate A, so it might be one of the others, and you know that'll help you. All right, now hit the refresh key on your on your and you keep talking. I'm going to start the question here. It's going to be alphanumeric, a code question. Here's your code table. Get an answer in. Why is it? Why can you eliminate options A, B, and D? Now don't type in T-bop. That's only an example. But figure out, and keep talking. And write it down in your notes. We're going to check some of the answers. And let me get it going. Okay, you can start answering your question. But think and talk. Be fruitful and multiply. Be fruitful and multiply your brain cells. That is what I want you to do. Aha, I hear clicking. I hear lots of clicking. The sound of brains. Clicking, clicking, clicking. Clickety-clack railroad track. Okay, I'll see you. How would you answer? I love to see you guys talking it over, which I can see you guys doing. and just gesturing at the codes, talking it over with your neighbors. I love that. It is a lovely sight to behold. Miss Ernavine. Yo, Miss Ernavine. Ernawine. Isn't that your name? Yeah. Did you get your answer in? Not yet? Still thinking? Good. I'm just practicing names, so. I can't remember your first name, but I can remember your last name. Pretty good, huh? TJ, get your answer in? Not yet? Still thinking? Got to put it all together. See, this is an area where you guys write the answer instead of me. Multiple choice, I give you some answers. You don't get any freedom with that. You just got to choose one of the things. This one, you can make it all up. Every single piece of it. 1 minute. One more minute. Oh my goodness. I so love seeing it. I truly do. I truly love to see it. Get your answers in. What's that? Did you get your answer in? Kinda. Okay. Yeah. It's a good workout. It's a good brain workout because it forces you to think, and and yet you have some freedom in how you express it, and that's actually what's difficult. How to, yeah. See, multiple choice is, you know, you can be pretty passive for multiple choice, but not for this. Okay, 15 seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Forsooth. Oh, wow. There's a bunch of you that put together. Wow, this is interesting. Let's take a look. And I haven't figured out an answer. I don't know what I would say, but here's some of the popular ones. A, B, P, C. Other options are smaller than. Actually, that's not bad. Other options are smaller than the correct answer. And that may be what's going through your head when you make the decision in favor of C, and because it is biggest. I didn't put anything bigger than that. All right, let's look at the next one. ABPU. Other options, smaller mass. Ooh. No, other options are smaller than mass. That is incorrect. Because that's like saying the other options are all newtons, but you can't compare a newton and a mass. You can relate them, but you can't say that, well, that's a smaller mass than this number of newtons. That's no good. You can't do that. Okay, A, B, and C. 14 people typed this in. Other options are N. Never correct. That's students. That's true, but it's not a reason. That's circular reasoning. I'm not saying that to be humorous. I'm saying that, and I grant that you may find it amusing, but and I'm not mad or anything, but it actually is incorrect to state the answer. So, to state what you already know as the reason is that's not an explanation. That's just a restatement of the question. And it sounds good, but it's no good ski. Uh, let's see. CRG, correct option, horizontal weight. No, CBG, sorry, CBG. I was going to say that. Okay, other options are weight. That's not, no, CBG, correct option is weight. Okay, that's a good answer. The whole, let me show you that one. Talk about that one. CBG, okay? You can see CBG is down there. 3 letters. It's 9 people typed that in. You're not wrong, but the question is, you know, how can you eliminate options A, B, and D if you, and the subtext of that, or the context, I guess, is that you don't know the actual answer. You know, CBG, correct option is weight. That's a statement from somebody that actually knows the answer. This one is for somebody that you're not really certain, but you can work your way through to an answer. All right, one more. Let's see this next one. Last one is PMWU. P is smaller than 10 times mass. You know, that's actually, that's not bad. Smaller than 10 times. And some of you wrote, you know what I would type in? Here's what I would type in. Maybe you want to type this in on your notes, or write this in on your notes. Correct option C, B is J multiple of M10 W times U mass K approximately. All right, so that's what I would have answered. All right, hit the refresh key. We got more questions coming up. All right, now we're working on specs. We haven't done the impulse yet. We're just going through some specs. All right, now this next question is going to be numeric. A calculation. Here it is. How far does it fall? In 0.25 seconds. Now this is not an impulse, but you may as well get this, get this locked in and, calculate it out. Go ahead and calculate that out. And as I said before, you can discuss and coach with your neighbor today, but not on October 22nd. Melanie, you got my message, right? Yeah. Yeah, no. Yeah, so tomorrow? Good. Yeah, we'll get something figured out. You know, that first individual that sent the email to both of us, that was like passive aggressive response. So I went right around that, and I sent an email to the dean, and So type in a number to the nearest centimeter. Okay, so centimeter is 0.01 meters. So to the nearest 0.01 meters of drop distance. Is that a... Are you using... Yo, in the second row, are you using flashcards? Wow. What do you got on it? What is the formula? All right. Yeah. No, it's all right, you know. I never used flashcards. You know, like if I'm memorizing something, you know, like a poem or something, yeah, I'll use flashcards. But like for physics, no, I never. 30 seconds. 20 seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2. You get it? No, don't look back there. Did you get it? Are you in? Did you get a check mark? All right. 3, 2, 1. Stop. I saw you clicking stuff in, so I thought, oh, I better slow down. I better put myself on kryptonite for a second there. All right. Because, you know, Superman, he always slows down when there's kryptonite around. He, you know, loses his powers. Whoa. Uh-oh. There's a lot of people with 0.31, which is correct. Good. Students, my wonderful students, hit that refresh key again, because we're switching back to multiple choice. Every time we switch modes, I gotta hit that. You gotta hit that refresh key. Next question. In 0.5 seconds, how far does it fall? So same kind of calculation. Thirty seconds. I see people clicking on their calculators. Excellent. Did you guys get it? Did you guys get it? Yo. Did you guys get? 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Dun, 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 dun. And you know what? 0.5, excuse me, 59% got the previous question right. 94% got this one right. Love. See what happens when your brain is awake? Excellent. Now, here's where it would actually go. If you kept everything to scale, it would look about like this, right down here. So it's quite a bit further. down than the previous picture at 0.25 seconds. And we're going to use that knowledge in just a few minutes. Now let's get to that main objective. Compute the impulse on the basketball in free fall with the time increment 0.25 seconds. And now we've got our specs, 6.08 newtons for the weight force from a mass of 0.62 kilograms, 620 grams, approximately, for an NBA basketball. And so now that you've got all your specs squared away, let's try one more question. Well, another question. We got a bunch of questions today. Okay, here's your impulse. Good. .62, 6.08, 1.21 gigawatts. You guys ready? 15 seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. 301. Wow. And you are mostly geniuses. All right. Shh, 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 shh. Friends, Romans, countrymen, lend me your ears. Here's the calculation. You use the delta P equals F delta T impulse equation, the impulse formula, and you plug in the weight force, 6.08, and the delta T, that's our study time, delta T is 0.25, and you just multiply those together. Now, here's something I want to point out to you. This is a Newton, and usually I write down a capital N when I have a force in there. But this time, I wrote it down in terms of a quotient of fundamental units, kilogram, meter, and seconds. And it's actually seconds squared. Now, the reason I do that is so that you can see how it cancels. And what cancels is the seconds squared cancels here, and then all the seconds up here. You're left with a second in the denominator, and so your final answer is going to be in kilogram meters per second. And that is what you want for a momentum. All right, so make a note of that. And there's no fancy name for kilogram meters per second. It's just kilogram meters per second. All right, it doesn't have a name like Sir Isaac Newton's last name or anything like that. And here's the numeric part. And that's the calculation. Now, just a side note to everybody, I worked out really carefully the proportions of basketball and vertical distance in this diagram. So it's a true to scale, all the diagrams in this series of questions. Now let me pause for questions from you before we continue. Yes. Yeah, mass times acceleration is 6.08. Yeah, so that's how you get the weight force. Yeah, the weight force is an example of F equals ma. Yeah, so another question? Yes. Delta P is going to be. Can you repeat your statement? Yeah, delta P is P is the symbol for momentum. I don't know why they use it, but it's customarily been P for many years. And so delta P is the change in the momentum or the impulse. Yeah, it's a change in the momentum. Of a net force is applied over time is going to change something about the momentum. Either its magnitude by slowing it down or speeding it up, or changing the direction thereof. If it's a centripetal. All right. I want to talk to you about strobe photos. Now, you can't just write down strobes for your notes. I want to think stroboscopically for a few minutes with you. And this is a strobe photo. It's a strobe photo of a person releasing a dove, I guess. And depending on the speed of your strobe, you can catch. See, the first image, the wings are upright, so that's like the middle of the stroke. Or no, actually, that's the top of the stroke. And then the wings are forward, that's the middle of the stroke. And then going out of the picture to the upper right, I don't know, it's kind of towards the end of the stroke, I guess. But I've looked at physics journals and stuff where they've actually mapped out the velocity field of a hummingbird using extremely fast stroboscopic equipment. Here's another one, kind of cool. These are all from MIT. There's a famous guy up there. All you have to do to see a ton of really cool looking pictures is type in strobe and MIT. And there's a guy up there, I think he's passed away now, Harold Edgerton. And he was a specialist in making ultra fast strobe photos like this for all kinds of applications. Not just cool looking photos, but because he always wanted to study the dynamics of things. He's a very interesting guy. And so what we're gonna, and this is actually a picture in one set of pictures. Time. You're looking at time. They say that time is a dimension, and you can kind of see it in these strobe photos. So let's think stroboscopically now about a vertical path. And again, I've typed this one now. This is a little bit smaller scale, so I can get everything easily onto one page. But this is the same basketball in two delta t 0.25 increments. Okay, so if you take a vertical path, and if you divide it up by equal increments of time, as we have done here in this picture, as we have calculated, and as you could easily do in PowerPoint on a Windows computer or Keynote, as I do on this Macintosh computer, you'll get a trajectory like that, and it's a lot like a strobe photo. Okay, it's not a strobe photo, but we've got it set up kind of to look like a strobe photo. And if you increment the path like that, you can say the following, that in each increment there's equal increments of delta p. In other words, the momentum changes in equal sized chunks. As long as you do your accounting in equal size chunks of time. So this is like mapping out your accounting on a per day basis. I'm sorry, my phone is. So day to day, you take a record of your accounting books, and you see the progress over time. Same thing here. Not day to day, but every quarter of a second, you flash your strobe, and you get an image like this. Now, the fourth comment is pretty important. The distance increments, delta y in this case, are not the same. Delta p is the same, but not delta y. And that is significant. Basically, we've got an accelerated system, so we have 1/2 gt squared going, right? Okay, and so those distances are going to get bigger and bigger. But delta p-wise, momentum-wise, yeah, equal sized chunks. Now, horizontally, in this particular case, there's no net force. So delta p is 0 horizontally. The only delta p that we get is vertical delta p. And as with Galileo breaking down or analyzing the motion of a projectile, we can do the same thing with momenta. We can analyze the horizontal component, and we can analyze the up and down vertical component. And in fact, there are 3 spatial components to momentum: px, py, and pz. And you can analyze all 3 of them. And what we're going to do now is analyze statement number 5 by looking at interactions of a set of box cars on a railroad track. So, and what we're going to do is look at box cars in the freight yard, and what they do is they get, they're forming a big string of railroad cars, box cars and flat cars, and all the different units of a train, of a freight train. They just assemble them, and they slide them down the rails towards the string of, and it locks up, and then they slide another one down the rail, and eventually the string of cars gets pretty long. All right, so that's what we're going to look at now. And here's the Northern Pacific Railroad, Northern Pacific Railway boxcar. It's a drawing of one. Let me ask you a question. If this boxcar is at rest in the freight yard, it's just sitting there, the velocity is 0. Does that mean there are no forces acting on it? No? No? If you say no, you have to tell me what forces are acting on it. So, okay, with the baseball hat, what forces are acting on it? Okay. That's right. You've got downward gravity, never disappears if you're on the surface of Earth. And if you're on a good rigid track, the ground or the track is pushing, is exactly bouncing. So this freight car, it doesn't have 0 external forces. It has 0 net external forces. All right? So here's our setup. First part is this. Oops, I got this out of order. Here we go. Okay, so the train goes in. These 3 are initially at rest. And this one moves in with a velocity of 4.4 meters per second rightward. Okay, so we're on a horizontal track, so we'll just go positive and negative for rightward and leftward. Okay, now the velocity of the group, though they're all 3 hooked together already, is 0. So V subscript G means velocity of the group. All right? And that's the initial state. Now, it goes in and it interacts right here. And those interaction forces are not external to the system of box cars. They're interaction forces. Okay? It's just like in free fall, if you jumped out of a perfectly good airplane, you could, within reason, I mean, there's a lot of air resistance, but you can still tie your you could pull a ripcord. It's not like you can't do anything else. You yourself your arms are interacting with your chute and everything like that. So you can pull a ripcord. You can button your collar if you got enough time. You can read the paper if it doesn't blow out of your hands. You can do some calculations on a calculator. You can do a million things if you're in free fall, okay? Even though you're accelerated. The same thing here. These are not, we would not call these external forces. Just as if you're in free fall, anything that you do in free fall would not be considered an external force. Okay, so pulling something out of your pocket on the way down, that's not an external force. All right. The same thing here. These, the string of 3 boxcars is going to push back on the one that's moving. The one that's moving is going to push on the string of, and they're both going to accelerate. Now, the acceleration on boxcar number 1 coming in from the left is going to be to the left. It gets a pushback from those 3 boxcars to the left. So it's going to have a little leftward acceleration, and in fact, it's going to slow down, but it's not going to stop. The other 3 are going to get an interaction force from boxcar number 1. So the group is going to get a rightward push, and they will accelerate slightly to the right. So the final state, however, they're all hooked together. And so now you're talking about a string of 4 boxcars. And I'm saying that these imaginary boxcars are 35,000 kilograms each. Okay, so that's a total of 4 times 35. Let's see, 4 times 35. 70. That's 140,000 kilograms down here in the final state versus a set of 35,000 here and 105,000 kilograms over here. But those are at rest, so they don't really contribute any momentum. All right, so let's figure this out. All right, now the total momentum before the interaction, so P subscript I, is simply the momentum of the first boxcar at 4.4 meters per second plus 3 zeros. Go ahead and write those zeros in. Normally you wouldn't want to, but since this is our first example, go ahead and write down 3 zeros. They don't contribute anything, except it contributes a little bit of meaning to the accounting that we're doing. We're trying to add up all the momentum assets in the system right now. And if you calculate that out now, 35,000 times 4.4, do you have your calculators out? Have you calculated that yet? 4.4 times 35,000. You should get, 154,000. Raise your hand if you verify it with me on that. Great. Okay, good. Yeah, always try to verify my calculations. Every once in a while I have a blooper, but now there's no net external forces. There's no horizontal gravity, as always, and the interaction forces are not external. They're part of the system, the boxcar system. All right, so there's no delta P. So that means that all the momentum afterward also should be equal to 154,000. All right, so make a note of that. And here's my next. I'll just move this up a little bit. All right, so my total beforehand is 154,000 kilogram meters per second. And afterwards, by P subscript F, final momentum, total. And this time, the definition of momentum says P equals mv. So the mass of my object is now 140,000 kilograms. And my speed, v nu, I don't know what that is. I'm going to figure it out, or we're going to figure it out together. And it's not that bodacious. But we have a system in which there's no net external forces. Yes, there are external forces, gravity and the rigidity force from the railroad track, but they balance. So that's squared away. Nothing horizontal. So delta P has to be 0. So before and after have to both be 154,000. And if you want to figure that out, V subscript nu, just divide 140,000 on both sides of the equation, and you get 154,000 divided by 140,000. And notice that kilograms cancel top and bottom here. I didn't put my little red strike throughs, but you can do that on your notebook. And that leaves me with meters per second, and then the numeric part is 1.1. Anybody verify me on that? 1.1? Question? It's 140,000 because down here I have four boxcars, and each one, and they're all hooked together, so they move as one big unit, and they're each 35,000. So, all right. Question back here. Yo. No question in the back there? Another question. All right, so this is your calculation. And my wonderful students, this is an example of something called the conservation of momentum. All right, the skateboarders that we had play patty cake up here in the front, those are also another good example of conservation of momentum. You know, they each exchanged the same amount of momentum, but their velocity states weren't exactly the same. We know all about that. Here's the basic idea. The total momentum of a group of interacting objects, and notice that they can be interacting. So the parachutist, on his way, he's interacting with himself. He's, emptying his pockets or, tying his shoelaces or whatever. The boxcars are interacting. The total momentum of a group of interacting objects remains the same in the absence of external forces. Write in net external forces. That'll be better. Because this one, the boxcars, yeah, they do have external forces, but they happen to balance vertically. All right. And if it's a good rail, you're not going to have a whole lot of friction. Though apparently those steel wheels with steel rails have very low friction if they use good quality steel. And so now we're going to be talking about conservation of energy, and in chapter 4, if you've read that, you're already ahead of things, but Thursday we'll talk about conservation of energy. But before we do that, let's try another example with boxcars, and you're going to calculate the question. All right, so one more quicker question. And I forgot to say hit refresh, but hit the refresh key because this is numeric. All right, now this is the same set of boxcars, but slightly faster initial speed for boxcar number 1. Let's see if you can work this out. All right, here you go. And let me start the question. Wow, we've had quite a few questions today. You guys are working hard. All right, take your time and definitely consult with your notes, consult with your neighbors. So the same 4 boxcars, but on another day, a little bit more speed, 6.4 meters per second. Na 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 na, la da 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 da, la da 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 da, la da da dum, na na na, na na, na na num, new new new, na na na. Na 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 la da 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 dum na 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 na. 45 seconds. I can't remember what the answer is. I didn't write it down. Let me think here. Mental telepathy. Twenty seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Come on, 301. All right, 300. Come on, 301. Yeah, baby. All right. Let's see what you guys got. Oh, my goodness. Looks like we got a bunch of geniuses in here. 1.6 is correct. Raise your hand if you got 1.6. Sweet. All right, that's a lot of people. Okay, now, seeing as how you guys are qualified as geniuses now, I'll dismiss early. Homework by supper time, if not sooner. Great class. You worked hard. Excellent. I'll see you on Thursday.